All right, good morning, everybody. Sorry, give me one second. Somebody is stuck in the waiting room here. Okay, great. The game plan today is to just keep going with our discussion on chapter 24 about Gauss's law. And remember, this is exploring the relationship between charge and electric field, but in this sort of formal mathematical way that we saw written down, and we'll look at again today. We will do a bunch of Gauss's law problems today. Try to get a feel for how that looks. There'll probably be some problems left tomorrow. I think we'll probably wrap up Gauss's law problem solving for this chapter probably halfway through the lecture tomorrow, and then I plan on leaving some time to discuss a little bit about any lingering questions you have on the first 3 chapters that we've looked at this semester, and also talk a little bit about the first written homework and what expectations are there. So that's the game plan. Are there any general questions before we get going while I get my screen share set up? Okay. If not, why don't we go ahead and get going? So just as a reminder, the main focus, really the only topic of this chapter, is Gauss's law. And we spent some time yesterday talking about flux, right? The definition of the flux. You can see that Gauss's law has a term in it, right? That's this thing E, the electric field, dotted into some little dA. That should look like a flux to you, right? This dA thing is this area vector that points normal to some surface, and E is an electric field vector. Okay. Q is just the amount of charge contained in some enclosed surface, and epsilon naught is our fundamental constant here. Okay. So the main focus for today is understanding this relationship, right? This basically says that if I sum the flux, the electric flux, over some closed surface, it tells me about how much charge is contained inside. And you can see that this side, right, if it's a positive charge, would be positive. So it tells me if the total flux around through some closed surface is positive, it means I have a total positive charge contained inside that object. And if the total flux, the flux is negative, it means I have a negative charge contained inside of that closed surface. And if it's 0, it means I have no flux. Zero flux means I have no charge contained inside of that surface. And let's just focus here for a second before we go to the problem solving on this structure. So why do we have to write it like EDA and then integrate over a surface? So we saw a bunch of examples calculating the flux for some uniform electric field that went through some fixed area. But we could also imagine that I had some scenario like this. So maybe I have a sheet like this, a window, and there's some electric field. And over here, the electric field maybe is tightly concentrated and tips in that direction. And over here, the electric field lines are very sparse. So the electric field is stronger on this side, right? Stronger on the left side of this sheet than the right side. And also the direction of the electric field is changing, right? Our general expression for the flux was E dot A, okay? But this assumes some uniform electric field. So the expression below is more general, right? This is saying if I want the total flux, right? If I want the total flux through some surface, what I can do is imagine finding the flux through a bunch of little windows and then summing those together, right? So what would that look like on this surface here? I could imagine breaking it into some small area that I'll call a dA, just a really small area. And I'm imagining shrinking that infinitesimally small so that the electric field through that little window is essentially uniform. Right, so then I know that the D flux through that window will be the electric field at that position, right, dotted into dA. So that's what we're doing here. We're basically going to say that if I don't have a uniform electric field over my surface, I can just imagine breaking the surface up into a lot of little flux windows, calculating the flux with our flux equation through each tiny flux window and just summing it up, which if you do that for infinitely small windows means you're going to integrate over that surface. Okay, so that's the idea. We'll see examples of how to set that up, and that for most cases that this integral actually isn't very scary, and we can do it pretty straightforward. Okay, so let's warm up by doing some simple problems where we're just trying to understand the relationship between the total flux through some closed surface and the amount of charge contained inside of it. So this one, we're just talking about the total flux through some surface. So there are three different cross sections for some 3D surface shown on A, B, and C here. So what we're imagining is, right, that they extend out of the plane, but we're looking at a cross section, and we see the field lines entering in the various directions indicated here. The question is, which closed surface or surfaces have zero electric flux in this example? Which ones have zero electric flux through that surface? Okay, I'm going to go ahead and end the poll. So most of you selected A here, which is the correct answer, right? I have some surface area here, and I could define some vector A, right? Here's my area vector. Over here, that vector, right, we said that this area vector always points away from, right, perpendicular to the surface and out from the center of a closed object. So the A vector is aligned like this across this object. So I can see I have on this side, I'm going to have some negative flux because the angle between, right, this angle theta between A and the electric field is going to be greater than 90 degrees, where over here it's going to be less than 90 degrees, but that's just going to change the sign of the two, so I get the flux canceling out through that object, right? We can also say it like we see the same number of electric field lines entering on the left-hand side as exit on the right-hand side. So I must have zero total flux for this object, right? For B, we see all of the flux is exiting the object and is going to be aligned with our A vector, so I would get a positive flux. And for C, we can see that we have more flux, right? All of this flux coming into the object, so I would have a negative total flux, right? It would have a component that's anti-aligned with my area vector. The perpendicular component would be anti-aligned. So the answer here is the answer here is A. Okay. What about this one? So I show a box now, and what I observe is that there's, say, uniform electric field that I observe coming through each of the 6 faces of this box. Can we say something about the type of charge that's contained in this box? If it's positive, negative, or no net charge? Let's see if we can figure that out. So let me know what you think. Is there a positive charge, a negative charge, or no net charge inside of this box? And just to remind you, remember our Gauss's equation says that the oh, sorry. Okay, so let's go ahead and stop the poll. So most of you selected B here, that there's some negative charge in there. Well, how are we going to determine that? Right? Gauss's law tells me I need to find the total flux flowing through that closed surface. And if it's positive, then it tells me that I have some negative, or then I have some positive charge enclosed. And if it's negative, I have some negative charge enclosed. Remember, my area vectors are going to point radially outwards, right, on all of these surfaces here. So I could draw they point outwards. So from the dot product, I know that on the faces where those field lines are pointing in towards the box, they're going to be anti-aligned with my area vector and give a negative contribution to the flux. So the total flux here is going to be the sum of, right, all my individual fluxes through each face, right? Flux 1, flux 2, all the way up to flux 6 through the last face here. And if I find that that total flux is positive in this case, then I know there's a positive charge inside, and if it's negative, I know there's a negative charge inside. And if it's 0, that means there's no charge. And look, this is a cube or a box, so I know that all of these areas are the same. So I know that for each of these terms, it's going to be like the electric field through that first face times A, and they're all going to have the same, right, the same A expression here, so that goes out. So I can factor that A term out, and it's just going to look like E1 plus E2 dot, 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 all the way up to E6. Where I have to assign the correct sign, right, this thing is going to be plus or minus depending on whether or not that electric field vector is pointing into or out of the board, right? The A vector is setting the sign that we're going to use on the electric field here. So I can just go through quickly. I see here I've got, right, when I put this into the flux contribution, I'm going to have something like minus 15A for the flux contribution here because it's pointing inwards. I'm going to have something like a plus 15A here. This one is going to be a positive. It's pointing outwards from the surface times A. This one is pointing inwards, minus 15A. This one's pointing outwards, positive 10A. This one's pointing inwards, so I have a minus 20A. And so now I just need to add up. Right now I have the sign and the flux here. They're all scaled by A, but I don't, right, the A is just some magnitude here, and I have the correct signs on all these flux contributions, so I can just add them up. So I can see that this minus 15 will cancel with this positive 15. I have a positive 20 and a negative 20 here, and then I have a negative 15 and a negative 10 for a total of something like minus 5 times the area. So I have a negative total flux, and based on Gauss's law, that tells me that I have to have a negative charge contained in the box. Okay. Oops. Did I calculate something wrong? Why does this say positive? Does anyone see that I did something wrong, or is my answer incorrect here? I think we may have the incorrect answer on the solution here, so I'll have to update that, right? I certainly see that there is, right, this guy canceling with this guy canceling with this guy, and then a negative total flux. So this is wrong. The answer here is that it's a negative charge inside of this box. Okay. So now we have to figure out how we're going to calculate this surface integral for Gauss's law. And we're going to use this trick that we said that if the electric field is tangent to the surface, then we know that the electric flux contribution is 0. And if the electric field is perpendicular and has the same magnitude E everywhere, then the flux contribution is just this simple E times A with the correct sign depending on the relationship between E and A. So let's think about this guy. We have a spherical Gaussian surface, two different spherical Gaussian surfaces here. On A, that the light shaded pink region is the Gaussian surface, right? It's a shell, a spherical shell surrounding a single charge or some charge Q that's at the middle. And in B, I have a spherical shell that's twice the radius, but with twice the amount of charge sitting inside of it. How do the electric fluxes between these two, or through these two Gaussian surfaces change? Which one has the larger electric flux through that surface? Oops, sorry, let me open the poll. Okay, we're answering which of the surfaces A or B has the largest flux through it. Okay, so most of you selected B, and that's the correct answer. Why is that? Because this thing here is the total flux, right? Gauss's law basically says that the total flux through the closed surface is equal to the enclosed charge over epsilon naught. So it doesn't matter what, right? The interesting thing about Gauss's law, or one of the interesting things, is that the shape of that surface that I choose isn't prescribed. I could have picked a spherical shell. I could have picked a smaller spherical shell as my Gaussian shape. I could have picked a oddly shaped, like, right, surrounding volume. And the flux through all three of those objects has to be the same. It's just related to the charge enclosed divided by epsilon naught. And since I have more charge in B, that means I have to have more flux through the surface that's enclosing the charge. So surface B has more flux. How much more flux? It has twice the flux going through it because there's twice the amount of charge. What about this one? I have spherical Gaussian surfaces with equal radii, and they're surrounded by spheres of equal charge Q. Which Gaussian surface has the larger electric field at the surface? Which one has the larger electric field? Right, we're trying to say something about the strength of the electric field at the surface of the Gaussian, at the surface of this at my Gaussian surface. Okay, let me go ahead and end the poll. Share the results. Most of you selected C, and that's the correct answers, right? Remember, the Gauss's law says that the total flux, which is E dot A, is equal to the total charge enclosed over epsilon naught. Well, in both of these two examples, we have the same total charge enclosed, right? It's distributed over, right? It has a different configuration, the charge, but all of that charge is enclosed in my Gaussian surface. And I have the exact same Gaussian surface, and I have the other key thing here is I have the same symmetries coming from those charges, right? They're both spherically symmetric, so that means the electric field is going to be spherically symmetric around those two objects, and so I expect to have the same flux from the same shaped field coming through that Gaussian surface, and so the strength of the electric field better be the same for both of those cases. They have the same electric field. What about this one? I have a spherical Gaussian surface and I have a dipole enclosed inside of it. Okay, so a positive and a negative charge. What can we say about this situation? Which of these statements is true? That the electric field is zero everywhere on the Gaussian surface, that the electric field is not zero everywhere on the Gaussian surface, or whether or not the field is zero on the surface depends on where the dipole is inside of the sphere. So we're trying to again say something about the electric field at the Gaussian, at the surface here. Okay, I'm gonna give you guys 5 more seconds. Let's close the poll. So we have some for A, B, and C fairly split. The majority of you, or most of you, thought that it was A, that the field is 0 everywhere on the Gaussian surface. So let's remember here that let's just keep writing down what Gauss's law says. It's E dot dA, and it's related to the total charge enclosed divided by epsilon naught. So what's the total charge enclosed here? Well, we see the total charge enclosed here, right? Q total, Q in this case would be positive Q minus Q would equal 0. So I have a net 0 charge enclosed inside of this surface. What does that tell me? That tells me that this guy better be equal to 0, and it tells me the total flux through that Gaussian surface should be 0. But does that mean that the electric field is 0 everywhere on the Gaussian surface? Well, certainly we can just visualize the electric field. We've seen the dipole before, and if I draw the electric field from a dipole, it looks something like this. Okay, we saw this back in the previous chapter. And we can just examine, we see that on the lower half of this surface, that I have electric field lines that are flowing into my Gaussian surface. And they're going to provide a negative flux. When I look at that, right, when I look at they oppose the direction of the area vector, that vector that points normal to the surface and outwards. And on the top, I see my electric field lines are going to be aligned with my area vector and are going to provide a positive flux. Okay, so the electric field is the same from the dipole as what we saw before. Okay. Gauss's law just tells us that the flux up here through this surface is positive and is exactly canceled out by the negative flux provided by the field coming in through the bottom. Okay. So the field isn't 0 everywhere. The thing that's 0 is the total flux. And the total flux can be 0 even though there are some positive field at the surface and some negative, as long as the total flux cancels out, right? As long as the amount of electric field entering the surface, I have the same amount of electric field exiting the surface. And notice that the flux being 0 doesn't tell me that I don't have charge inside of my object. It just tells me that the net charge is equal to 0, right? So I could have a bunch of positive and negative charges inside of my surface, but as long as they cancel each other out, when I do that flux integral over this surface, I should end up with 0. Okay, what about this guy? The electric flux is shown through 2 Gaussian surfaces, okay, in terms of some charge Q. Can we determine what the charges are on Q1 and Q2? Oh, so I have a typo here. So let me add a label here. Let's call this one Q2. Okay. Can we determine what Q1 and Q2 have to be? So let's stop sharing and relaunch. So this one, you're going to have to do a small calculation. Let's see if you can figure out how the charges are related. Okay, I'm going to give you a little bit more time since this one takes a little bit of a calculation. Okay, I'm going to go ahead and stop the poll. So some of you picked A and some of you picked C. It was fairly even split and a few other answers here. Right, well, what they provided me is the flux through the surface, right? We know the total flux through the surface is equal to the charge enclosed. Oops. Let me erase that. Is equal to the charge enclosed times the divided by epsilon naught, right? So this has got to be Q enclosed divided by epsilon naught. Well, I know for this orange surface here, what's the Q enclosed in that orange surface? Well, Q2 is not inside of that orange or peach surface. It's only Q1. So this tells me that this top expression I could write down should say 2Q over epsilon naught is equal to Q1 over epsilon naught. And for the gray Gaussian surface, I can play the same game. This says that Q over epsilon naught, that's the flux, should be Q1 plus Q2, because now they're both contained inside of the Gaussian surface divided by epsilon naught. So I can see from my top expression here that Q1 has to be equal to twice Q. And then from my lower expression here, I know that Q1 is equal to twice Q. And so if this expression is going to hold, I need that Q2 has to be minus Q. So I get that the answer is C here, that Q1 has to be twice Q and Q2 has to be minus Q. Okay. Now that we've done some sort of quick problems trying to understand sort of the ideas of Gauss's law, let's try to do a more complete Gauss's law calculation. We're going to do a few of these for however many we can get through for the rest of the time, and then we'll just pick up here tomorrow. So what we want to do is we want to calculate the electric field outside of a sphere of charge. And in chapter 23, we just asserted that the electric field outside of a sphere of total charge Q is the same as the field of a point charge at its center. Let's use Gauss's law to prove this. Okay. So I'm going to try something a little bit different today. I'm going to try to push the slide over to the side and write on this so you guys can see. Maybe you still read the problem over there on the left here. Okay. So how do we set this up? Let's start by making a diagram. Okay, so we have a sphere of charge, right, that has, say, some radius r, and it has some total charge q associated with it. Okay. And we want to find the electric field, what the shape of the electric field looks like outside of this sphere of charge. Right? So we want to know, what is the electric field, say, as a function of the radius r, as long as r is greater than big R. And we want to use Gauss's law. So Gauss's law tells us that we need to integrate the electric field over some surface area A, right, this surface vector A, and that should tell us about the total charge enclosed in that Gauss's surface divided by epsilon naught. So in order to do this surface integral, first we need to pick a Gaussian surface. Pick a Gaussian surface. Right? This surface is some free choice. This is just, right, these Gaussian surfaces are just mathematical tools. So we're free to pick any Gaussian surface we like. But what we're going to do is we're going to argue that there are some Gaussian surfaces that are better than others because it'll make calculating this integral more straightforward. And here's the argument we're going to make. We're going to evoke this idea of symmetry that we talked about yesterday. We see that that's a sphere of charge with, right, some uniform sphere of charge, so there has to be some spherical symmetry to the electric field. Right, if I take that charge distribution, that sphere of charge, and I rotate it in any direction, I can't tell the difference from that physical object, so the electric field should follow the same, right? So that means I know that the electric field at some radius should point radially outwards and should be at a constant magnitude, right? As long as I'm at some fixed radius, the electric field points outwards and is uniform. So then I'd like to use a Gaussian surface that exploits that symmetry. So I'm going to pick a Gaussian surface that has that same spherical symmetry. Okay. I'm going to pick, say, just a sphere, okay, that has, say, radius, let's call it r prime, something like this. And I drew it very badly here, but let's imagine that I had centered that on this sphere of charge. Right? Well, if that charge is sitting right at the center of a spherical Gaussian surface and I have this spherically symmetric electric field pointing outwards, then I know that everywhere this electric field has to be perpendicular to the surface, and I know that that electric field has to be uniform, or it has to have the same value everywhere on that surface. And that's really nice for this Gaussian integral, because if E and dA, right, this is telling me, remember, my dA is pointing outwards and perpendicular to the surface. So that means because I picked this spherical Gaussian surface, I know that my dA and my electric field vector are aligned. So I can already make this integral just E dA. I can get rid of the dot product because I know that the angle between dA and E is going to just be 0 everywhere, and the cosine term for that dot product is just going to be equal to 1. Okay. Furthermore, we just argued that the electric field is uniform everywhere and constant at that fixed radius, so I can pull that electric field outside of this integral because it's just going to have a fixed magnitude at that particular radius over the entirety of the surface. And now that integral that I have here, right, it says just integrate all of the tiny little area contributions that you're going to have over the surface. And that's a very easy integral. That just gives me back the total surface area of that Gaussian surface. Okay. And now I'm almost done. Well, what is the total area of that surface? Well, it's a spherical surface, so I know what that area is, right? It tells me that the electric field, the area is going to be 4 pi r prime squared, and that has to equal Q total over epsilon naught. And now I can just solve this expression for the electric field. This tells me the electric field is equal to Q total over 4 pi epsilon naught divided by r prime squared. Okay, look, it's just cool, the form that we saw from a point charge, right? If I had, so nowhere in this problem did we have to use the fact that the charge inside of this object had a radius of r, right? That charge distribution. So this would have worked for a point charge. It would have worked for a very small sphere or a very large sphere, as long as it was totally contained inside of that spherical Gaussian surface. And you can see that it just follows that form before, right? It looks like the functional form that we saw for the electric field coming from a point charge. And so we proved with Gauss's law that a sphere of radius r, that outside of that sphere, the electric field looks identical to what I would get from a point charge sitting with the same charge at the center of that sphere. And I also want to point to one other thing. We had this discussion a while ago that, right, this thing that we would write this sometimes like k q over r squared, right, where k was 1 over 4 pi epsilon naught. And now you can see why we move to this 4 pi epsilon naught, because Gauss's law has this fundamental thing that epsilon naught is just some constant that sets the scales and the units between the flux and the charge enclosed. And that 4 pi term, that 4 pi that we saw coming in the k, comes from the spherical geometry or the spherical symmetry. It has something to do with the geometry of the situation. Okay. And so that's why we expressed it in terms of these factors of epsilon naught. Okay. Okay. All right. This is all just what we saw. Well, sorry. Okay. So let's continue that. What if we ask instead for the electric field inside of a sphere with uniform charge at some fixed radius? Okay. How is that going to change the problem? Well, let's jump back into our work problem here, into our workbook. So let's set this up again. So again, we're going to have a sphere, and it's going to have charge Q. And what we want to know is, what is the electric field at some radial position, say, inside of the sphere here? What is the electric field at this position R? Right, we want to know what ER is at some position where R is less than the, say, the radius of this sphere. Okay. Well, again, we see that there's radial symmetry here. So we expect the electric field, if I pick, right, so I'm going to use that same argument I did before. I'm going to pick a Gaussian surface that just is spherically symmetric around the center of this thing. Okay. Because I know that the electric field should follow the symmetry of the charge distribution, and because we're assuming that there's uniform charge filling this thing, right, that the underlying charge sources are spherically symmetric, and so should the field be. So what does Gauss's law tell us here? It tells us that if we integrate E dot dA, I should get the total charge enclosed divided by epsilon naught. Well, let's work on the right-hand side a little bit here. What's the total charge enclosed in my sphere here? Okay. Inside, this is the total charge enclosed in my Gaussian surface. So how am I going to calculate that? Well, I know that I can calculate, say, the charge density for this object. Right? The charge density of the sphere is just going to be the total charge on that sphere divided by 4/3 pi r cubed. Right? I'm just taking the total charge, right? This is the charge divided by the volume. So I can find the charge density on this sphere. And then the total charge enclosed then is just going to be that charge density times, right? This has got to be equal to the charge density times the volume of what? Of my Gaussian surface over epsilon naught. What's the volume of my Gaussian surface going to be? It's going to be 4/3 pi little r cubed, right? Just the volume of a sphere over epsilon naught. Okay, so that's the right-hand side. What about the left-hand side here? Well, again, we can use the same arguments we made above. The electric field is got to be radially outwards and constant because of the spherical symmetry. So it can pull outside of this integral. And then I'm just going to have something that's like the total area of my Gaussian surface sitting on this side. And I know what that total area is. That's just going to be equal to, right? That's just going to be equal to my 4 pi r squared, right? That's just the surface area of that Gaussian sphere. And now I can just solve this for the electric field. This tells me that the electric field, I see these 4's are going to cancel out. I see these pi's are going to cancel out. I have r squared over here. That's going to leave one factor of r on this side. And I end up with an expression that's like the density, the charge density of the sphere times r over epsilon naught. Okay. So the magnitude of that field is related to the charge density and how far away I am radially from the center of the sphere. And you can see that, right, this would have been more challenging to solve by like doing a bunch of integrations over, right, like breaking this thing up into a bunch of point charges and calculating all of the contributions, right? The nice thing about Gauss's law is I can just ignore all of the charge exterior to my surface, and I know that it doesn't contribute to the flux through my Gaussian surface. Oh yeah, what about the 1/3? Thank you, there is a 1/3 here still. Yeah, the 1/3 is still there, thank you. Okay, but we end up with a pretty clean, right? For a pretty minimal amount of work, we get a nice functional form for the electric field. Let's try one that's even a little bit more complicated. Let's try this this other one that's here on the slide, the second bullet. What about the electric field inside of a sphere that has a charge density that's equal to some constant divided by 1 over r? Let's see if we can do that. So first of all, oops, we can draw a picture of this thing. Again, I'm just going to have a sphere of charge. And now they tell me that the charge density isn't uniform, that it looks something like this. It has a radial dependence, and it looks something like C, where C is just some constant divided by R. Okay. So Nicholas is asking in the chat, should you memorize these functional forms for the chart, for the field inside of a sphere and outside of a sphere? I would say no. I mean, if you want to, that's fine. On any of my exams, you'll have access to an equation sheet, and those can certainly be on your equation sheet if you would like. Okay. The key thing here I want you to focus on today is just the technique I'm using to solve for these fields. All right, so first thing, let's calculate what that constant C has to be. Okay, well, how am I going to do that? Let's say that there's some total charge Q, right? That if I sum up all the charge on this thing, that it's this thing Q. Well, that means I know that if I integrate, right, how do I get that total charge Q? I'm going to integrate the charge density times some small dv, and that better give me the total charge that's built up on this object. That just means I'm integrating that right, this thing, right, this is my r-dependent density. I have to integrate that thing over r. Well, what is this dv thing here? This is a little differential volume. And since we have spherical coordinates here, and we have, right, maybe you can remember back to your calculus that dv thing, right, this is like the density of r, looks something like sine of phi r squared sine of phi d phi d theta dr, something like this, right? This is a three-dimensional integral that I have to do over this thing, right? I have to integrate this thing from say 0 to r, where r is the radius of the sphere, from 0 to 2 pi, and from 0 to pi for my different angular terms. And this really just boils down to something pretty straightforward, right? This is just going to give me that this, right, so I can split this up into the integrals over the angular pieces and the radial pieces. The angular pieces are all very straightforward to perform. And if you remember back to your calculus, there's a standard metric that we get, right? A standard differential that we can use if we have spherical symmetry in my in my system. So this thing is just going to be equal to the integral from 0 to r, this density, and then I'm going to have dr here, and then I'm going to have a, oops, I need to make some space here. And this thing is going to be like 4 pi r squared dr, something like that. And now I can pull out that 4 pi part. What is that density? What is the density? I know that's like c over r. This guy here is r squared dr. I'm just plugging in the functional form of my density here. And so this is like the integral from 0 to r, 4 pi cr dr. And now this is a pretty straightforward integral to do. Right now I just have a one-dimensional integral. And when I do that one-dimensional integral, I'm just going to get something that's like 4 pi over 2 c r squared, well, big R squared, something like this. Okay. And this has to equal my total charge on that sphere. So I can solve then, and I can see that c, right, is just something that's related to the total charge. It's the total charge divided by 2 pi r squared, something like this. So that c, right, the point of this, right, I'm not expecting you guys to be experts at three-dimensional surface integrals. The point here is that because of the symmetry, you could go remind yourself back in a calculus book that that integral is really just a one-dimensional integral, right? It has to be one-dimensional because there's this spherical symmetry, so there's nothing interesting happening in the angular direction. And that dv term for spherical symmetry always just has this functional form, and you can convert this into a one-dimensional integral and get something like this. Okay. So c is just some constant, and it's related to r squared. And now that I have that c, right, now I want to apply Gauss's law. So now I need to define a Gaussian surface. So here's my Gaussian surface. Again, let's say that it has radius little r. And it tells me, right, again, I'm going to use this. I still see that I have spherical symmetry. So I know the electric field at that radial position r times 4 pi r squared, that's the surface area of r, has got to be equal to the charge enclosed in that Gaussian surface divided by epsilon naught. And now what's the charge enclosed in that surface going to be? Well, we know what that has to be. E is going to be 4 pi, right, this thing. The charge enclosed is going to be the integral from 0 to r dr, oops. C over r squared 4 pi dr. Okay. And when I do this again, and this is all over epsilon naught. And when I do that, I just get something that's going to be like 1/2. Now c, I know what c is. It's this thing q over 2 pi big R squared. Okay. And then I'm going to have this bit that's going to be like 4 pi. Then I'm going to get another factor of 4 pi here. And then what do I get? And then I'm going to have r squared, something like this. All of this over epsilon naught. Okay. And now let's simplify this. We're trying to solve for E, right? We're trying to solve for E. So this is equal to E, oops, E 4 pi r squared. And some things cancel. Look, I have an r squared factor on each side here. I have a 4 pi on each side here. And so I get that the electric field is just equal to Q over 4 pi r squared epsilon naught. So I know it was a little bit of a complicated journey to get there. We went through these surface integrals, but right, these three-dimensional integrals. But really, if we look at this, right, it's really like, I don't know, like just like a few lines of calculus, right? You would have to go back and remind yourself about your three-dimensional calculus. And we get this really interesting answer, right? It says that the electric field is independent of how far away I am from the center of the sphere. Look, it doesn't depend on little r anywhere here. I have a uniform electric field inside of this volume. No matter how far I am away from the surface, I have the same electric field strength. It doesn't depend on, right? It doesn't depend on the radial distance away, okay? And that's an interesting result, and this is just an example of, if you tried to calculate that using the electric field superposition principle that we saw last chapter, the math for calculating that would be, I don't know, would be like 20 times longer than this. And so even though I know that this calculus might be scaring a few of you guys, and I want to rest assured that I'm not going to expect you on an exam or homework to do a complicated three-dimensional surface integral, the point here is that by exploiting symmetries and using this Gauss's law, that we can calculate electric fields fairly quickly using this principle, okay? So we're gonna pick up, we're gonna stop there for today. We'll pick up with this idea tomorrow. We'll do a few more examples of calculating the electric field from different kinds of geometries, and we'll go back to some simpler ones. We'll rederive, say, the electric field from an infinite line of charge and from a sheet of charge, and see that we can do that very quickly using Gauss's law. Okay, that's it for today, guys. I'm happy to take questions if you have a question or two before you take off.